All right. Thank you, Cheryl, and thank you to Professor Shi and others who gave me this invitation to share some of our ongoing work here at UCLA. So today I'm going to be talking about seismic risk and resilience modeling of water distribution systems. And much of the work, actually all of the work here, is work that was done by my former PhD student, Agam Tomar, who is now a research scientist at Johnson & Johnson. So this gives sort of an overview of the presentation. I'll start by highlighting sort of the importance of water networks in the broader and the broader implications for earthquake damage and disruption. I'll talk a little bit about an end-to-end simulation model that goes from hazard characterization all the way through functional recovery modeling. I'll talk about conducting risk-based assessments where we consider not just one event, but the full suite of events that could affect the region under consideration. And then we'll talk a little bit about how we can use data collected during the recovery to update our estimates of the same trajectory. So I think we can all appreciate the important role that water networks play in our society. One of the critical roles, which is especially important here in California, is that it's a big part of it's a critical part of the infrastructure that's needed to fight fires, including wildfires as well as fires within buildings. When you think about buildings themselves, you know, there's the functionality of the building that is underpinned by different utilities, and water. The water system is one of those. And then water systems generally support not just residential buildings, but a variety of different operations, including commercial, educational, and industrial. And so if you think about the implication to the physical damage and functional disruption of a water distribution system, it can lead to cascading effects. We know that a lot of our critical infrastructure are highly interdependent, meaning the damage or disruption within one system can propagate to functional losses within other systems. And given that water systems are, or given that pretty much all of our critical infrastructure is relying on water systems, there's sort of there's this tendency for this cascading type of failure if you have damage to water distribution systems. So one of the things we've been doing is thinking about developing what we call an end-to-end simulation model for water distribution systems. Sorry, I'm just trying to get rid of this icon. Sorry, I'm just gonna do something here really quickly so I don't have to apologize for the. So let's see. Move that over there. Okay, is the slideshow still? You can see the slideshow?
Yes, we can see it great. Thank you.
Okay. And I will move this over here. Okay, sorry about that. I'm just trying to make sure I can see my slides properly. Okay, so we've been, one of the things we've been working on is creating what we call an end-to-end simulation system. And the application or the context in which we've developed this end-to-end simulation model is for water distribution systems, but the framework itself is actually applicable to other types of infrastructure systems, including electrical system, transportation systems, and the like. So just to give an overview of the system, so as with any other type of assessment, you would define the system itself. You would define the topology, the components that actually make up the system, and then to be able to capture the relationship between the loading intensity that's generated by whatever hazard you're considering and the physical damage. You need component fragilities, but you also need, in the context of resilience, where there's an intentional focus that's placed on recovery. You also want to define the resources that are available to carry out that recovery. And so, given an appropriate type of model, you can simulate the physical damage at the component level, and then you need to have some type of mechanism for taking that physical damage and sort of converting it to disruptive incidents, right? So for example, if we're talking about a water distribution system, what does it mean for a pipe to be leaking or broken? Well, it means that it's going to affect the hydraulic pressure within the pipe, right? So we want to be able to go from physical damage to functional disruption, as well as the recovery activities that are involved in that disruption in the restoration. And we do that using a Python-based discrete event simulation model, which I'll talk about a little bit. Now, we want to be able, so then the question is how, so we've simulated the physical damage, and we've sort of quantified what does that mean in terms of a disruptive incident, as well as whatever actions needed to bring about recovery. And so the question becomes now, how do you measure functionality of the system? Well, this is a water distribution system, and in this particular case, we're actually using a hydraulic simulation to measure the loss of service to the region that is serviced by the water distribution system, and we're doing this using hydraulic simulation. We're actually not doing the hydraulic simulation ourselves. We're relying on a tool that was developed by Sandia National Labs, water network tool for resilience called Winter. And so there's a package in there. There's a Python package in there that actually does the hydraulic simulation for us. So what we're doing is we're linking the physical damage, the physical and functional damage to the water network, to the hydraulic simulation tool developed by Sandia. And that allows us to understand sort of the hydraulic performance of the system over time. So once we're able to do that, then we can simulate both the physical and functional recovery. So the physical recovery would be the repair of the damaged components, the repair of pipes, the repair of broken tanks, and then the functional recovery would be the restoration of service provided to the affected region. And then, given that we can model not just the initial loss of function, but the restoration of function, we can take that and use it to compute metrics that can be used as the basis for decision making. So a lot of the work that we've done has used the Napa water distribution system as a test bed. There was an earthquake that happened in 2014 in South Napa, and it was a moderate earthquake. The losses that were sort of attributed to the earthquake range anywhere from about $500 million to $1 billion. But there was damage to the water distribution system. And the Napa Water Division, which is responsible for managing that water network, they were generous enough to share information with us, not just on the topology of the system, but also on the damage that happened in 2014, as well as the duration of the repair process, meaning repairing broken pipes and things like that. So we actually were able to get a robust data set that we used to be able to validate and evaluate our models. So this slide just gives an overview of the Napa water system. It serves about 88,000 people via 25,000 connections. There are about 600 kilometers of pipes, 15 tanks, 10 pumping stations. I mentioned before that the relationship between the loading intensity, in this case, we're looking at earthquakes, but as I mentioned before, the framework that we developed is applicable to other types of hazards and also other types of infrastructure systems. But to link the loading intensity, in this case, shaking intensity, to the physical damage, we need component fragilities. And for the pipes, we actually were able to develop our own fragilities using the data that was provided to us by the Napa Water Division on the distribution of damage to the various pipes. So we developed our own pipe fragilities. And then the fragilities for tanks and pumps, we relied on sort of prior resources. I mean prior sources like hazards and things like that to come up with those numbers. We also, the model also needs recovery resources. So what are the repair materials that are on hand? What is the availability of inspection and repair crews, and how does that change over time, right? We know after the 2014 event that that the city of Napa got a lot of support from surrounding counties. So in terms of resources, we want that to be reflected in the model itself. So without going into too much of the details, because simulating the spatial distribution of damage, of earthquake damage, for some given scenario, it's a pretty well established sort of workflow. So given the spatial distribution of shaking intensity, coupling that with our fragilities, we can simulate the spatial distribution of damage. So the next step in the process is, okay, so now we have, now we've simulated the damage to the various components of the network. Now we need to specify, okay, how does a state of damage to a particular component relate, how does that relate to a disruptive incident? And then what are the restorative actions that are needed to restore the functionality? So in terms of disruptive incidents, so there's pipe breaks and leaks that cause water loss and reduce pressure. Similarly, damage to tanks also causes water loss and reduce pressure. And then for the pump, that actually leads to reduced water pressure, because as we know, the pump is what, unless you have sort of a gravity flow, the pumps are relied on to move the water through different parts of the system. In terms of the recovery action, so when things get damaged, we need to acquire the materials that are needed to do the repairs, unless you have a stockpile at hand, and the model can accommodate that as well. Obviously, you need to do inspections, repairs. There are various other activities that are done during the recovery process to minimize the amount of water that's lost, like rerouting and isolating various junctions and things like that. The last two, our model actually did not consider. We did not consider these things because these were not things that were sort of prevalent after the 2014 earthquake, but these could be easily incorporated into the model. So given the state of damage to the system, we now want to take that and turn it into a functionality metric. What does it mean? So now that we have earthquake happens, there's damage to pumps, pipes, etc. What does that mean in terms of the ability of the system to provide water service to the affected region? And for that, we use the system serviceability index. And really all that is, it's for each of the junction we're normalizing the actual water that's supplied at a particular node by the demand to the node, and then we're sort of aggregating that over the entire system. So I mentioned we use a discrete event simulation model to model the restoration processes. We use this type of model because it's a good model for mimicking real life processes. So if you want explicit representation of various activities that need to happen within a disruptive system, within a system that's disrupted and needs to be restored, the DES model is not the only type of model out there, but it's a good one, and it's the one that we went with. So what's shown here is a simple DES model for pizza delivery. And the three of the main components for any type of DES model are the entities, the resources, and the processes. So in this case, the entities are the restaurants, the customers, and the pizza. The resources are the drivers, and the process is the ordering of the pizza by the customers and the delivery of the pizza by the drivers, right? So if we put that into the context, if we put the DES model in the context of the water distribution system, then the entities these would be the physical components. So it would be the pipes, the pumps, the tanks, the reservoir. The resources would be the things that are needed to bring about recovery. So the repair materials, the inspection and repair crews, and then the processes are the activities that are needed to bring about, to restore functionality. So inspecting damaged components, repairing them, and then any isolation or rerouting that's done are also part of these processes. So I mentioned before that the Napa Water Division shared some data with us, not only on the physical damage, but on the trajectory of repairs that happened over time. And this is specifically pipe repairs. And so one of the things we were able to do is this is not it shows sort of a good comparison between the empirical and the simulated model. This is not a blind simulation. This is more just for us to sort of tweak our model parameters to make sure that we're at least getting a somewhat realistic representation of the repair trajectory for the pipes. Now, keep in mind, this is the repair trajectory. This is not the functional recovery trajectory, but we did do this comparison because this was sort of we had information on how the pipes were repaired over time. As you'll see later, we did not have information on how the hydraulic performance changed over time. So we were not able to verify, to validate that side of things. Okay, so I mentioned before, so the previous slide was sort of the restoration of physical damage. Here we're looking at the restoration of functionality. And again, we're quantifying functionality using the system serviceability index. So, so what's shown here are restoration curves for a single scenario where we're considering multiple sources of uncertainty. So we're considering the uncertainty in the hazard, by simulating joint distribution of shaking, and we're sort of doing a Monte Carlo simulation to get multiple realizations of shaking over the region. The fragility functions allow us to account for the uncertainty in the physical damage, and then we're also considering the uncertainty in various restoration parameters, namely the crew size as well as the event duration. And by event duration, I mean the time it takes to perform repairs, the time it takes to do inspections and things like that. So if we go back to the figure, each light gray line represents a recovery scenario for a single realization. And again, we're doing this end-to-end simulation using a Monte Carlo approach. So if we consider all of the sources of uncertainty shown in the right, we would have multiple realizations of recovery. And then the black lines represent the central tendency, and then the 60th and 84th percentile of the recovery. So now, we want to think about what type of information that can we provide to, say, like a decision maker. So for example, the Napa Water Division, in such a way that they can actually use it to make decisions, right? So you wouldn't hand over the type of plot that's shown here on the left to someone who is unfamiliar with these types of models and expect them to use it to make it a decision. You sort of want to summarize the information in some way, right? And so what's shown here is sort of a schematic recovery curve that shows the different types of metrics that we can use to quantify the overall performance of the system. So we can look at the immediate loss of system serviceability. That's sort of a representation of the robustness of the system. We can look at the time to reach a particular SSI level. In this case, we're looking at the time to reach 100%. And you can also look at the cumulative loss of serviceability, which is basically taking the area above that recovery curve and normalizing it by the entire area represented by the rectangle. So again, so now given that we don't have just one recovery realization, we have a suite of realizations that sort of incorporate all of the various types of uncertainty. The question is, what type of summary metric can we use? Well, one thing we can do is we can say, okay, what's the probability distribution of the time it takes to restore to a certain level. So for example, here, I'm taking a slice at about the 90% SSI level, and we can look at the distribution of the time it takes to get to that 95% or 90% pre-event SSI. And so what's shown on the upper right is just a histogram showing the empirical distribution. And what's shown on the lower right is a CDF, a cumulative distribution function of the time it takes to restore 90% of the pre-event SSI. And so now with this, we can ask questions like, well, what's the probability that the time to restore the 90% pre-event SSI is less than some numbers. So for example, we can look at 180 days or 6 months, and we see here that it's about a 42% probability that we would restore 90% of the SSI within 6 months. Okay, so the last few slides focused on a single scenario, right? So we took a single scenario. In this case, we focused on replicating the 2014 event. We run it through our end-to-end simulation model, and we're able to quantify these different resilience metrics in a probabilistic manner. We also did a risk-based assessment where we considered not just one event, but the full spectrum of events that could affect the region. And you'll see later on that allows us to look at things from more of a life cycle perspective. So this is just the overall workflow for the risk-based assessment. So the first thing you need to do is to define the catalog of events that can affect the region or that can have a significant impact on the system. And for that, we use the USURF3 model. These rupture forecast models are sort of evolving over time. The latest one is actually the USURF3 model, but at the time of this study, we used the USURF2 model. From that model, we can generate a ground motion map from each event. And for every ground motion map, we can sort of run through our end-to-end simulation in the way that I just outlined in the previous few slides, right? And so here we're just showing for the USURF2 model and for the region under consideration here, we're talking about Napa. We're talking about 2,300 events. And for each event, we'll look at 50 spatial correlated ground motion maps. So that adds up. And then for each for each event, we do 1,000 simulations where we randomly sample from the 50 spatially correlated maps, and we simulate damage, and then the full end-to-end simulation on each of those. So the computational expense starts to add up, but as you'll see later, there's ways to sort of get around that. Okay, so given that we're considering all of the possible events as well as their annual exceedance rates, one of the things we can compute is the annual exceedance rate for a specified network performance level, right? So what's shown here is the basic equation for that, where the WJ is just the annual rate of exceedance for the map, and the I is an indicator function for the network performance level exceeding some predefined threshold. So if we go through that process, we can get, well, one thing we can get is we can get this type of plot shown on the right, which shows on the horizontal axis any one of our resilience metrics. In this particular case, it's the immediate loss of SSI. On the vertical axis is the annual rate of exceedance. Well, that annual rate of exceedance number is not really a number. It's not a very intuitive number. So one of the things you can do is you can say, well, okay, what's the probability of exceeding some level of immediate loss within, say, a 100-year period. So I mentioned before that one of the things you can do here is look at it from a life cycle perspective, right? So you can look at what's the probability of exceeding some level of loss within a 100-year period. And for this particular system, we found that there's a 6% probability that the immediate loss exceeded 50% within a 100-year period. This shows a similar plot for the time to restore 100% of the pre-event SSI. And what we're seeing, the result we get here is that there's a 26% probability that exceeds 90 days, meaning there's a 26% probability it takes more than 90 days to restore 100% of the pre-event SSI over a 100-year period. And here's a similar metric for a similar result for the cumulative loss of SSI. So one of the things we wanted to do is we wanted to look at, okay, so I mentioned before, we consider all these different sources of uncertainty, the uncertainty in the hazard, the damage, the restoration. And so one of the things you would sort of want to think about as someone who's managing these systems is if I have to spend, say, time and resources and money to sort of reduce this uncertainty by collecting additional information, where should I focus my effort, right? And so one of the things we wanted to do is disaggregate the overall dispersion by the source of uncertainty. So that starts to tell us, okay, where is most of the uncertainty coming from? And as you'll see later, it depends very much on the metric that you're focused on, right? So what we did is we took a single event and we ran 100 end-to-end simulations. And first we considered all the sources of uncertainty, and then we considered one source of uncertainty at a time. Right, so let's say we'll consider the uncertainty and the hazard, and then we'll fix the damage and restoration parameters at the median value. So the plot that's shown here is the one where we consider all sources of uncertainty. So you see sort of the plus or minus 1 standard deviation bounds on the SSI curve, and some basic observations here. We can look at the coefficient of variation in the various performance metrics, and we see that the dispersion and the time to restore 100% SSI is the highest. And that sort of makes sense intuitively, because usually early on in the recovery process, there's this sort of concentrated effort. And then once things get to sort of 90%, 95%, where most of the functionality is restored, then you sort of, then it's okay to sort of take time to sort of maybe even improve the system or do things that could improve the system for future events. So sort of getting back to the 100% might take a little bit longer, or there's a lot of variation in the time that can take. So what's shown here is sort of how the bounds of the restoration curve would change when we consider one source of uncertainty at a time. So the one on the far left, we only consider the uncertainty in the shaking intensity. The one on the far right, we only consider the uncertainty in the process durations, and then the damage fragility and the crew size are in the middle. And sort of one of the key results sort of jumps right out at you. Jumps right out at you is that the crew size, especially in the later stages, plays a major role. And so what that's telling us, again, that's sort of consistent with what we understand, in that in terms of right after the event, there's sort of a concentration of effort in terms of inspection and repair crews, and then over time that it sort of drops off. And so there's a lot more uncertainty in how long things are gonna take. But if we look closer, we can see that again the type of uncertainty that dominates depends very much on the metric. So for example, at low levels of at lower pre-event, the lower pre-event SSI dispersion is actually dominated by ground shaking intensity, whereas if you're looking at higher pre-event dispersions, it's dominated by the crew size. And again, that makes sense, because at the lower pre-event SSI levels, most of the SSI is dominated by the damage that actually happened, and that damage is going to be affected more by the shaking intensity, whereas later on, you're going to be affected by sort of how you schedule your crews to do the repairs. And in general, the dispersion increases as the pre-event SSI increases, and then the process duration has the highest uncertainty in the very tail end. Okay, so I mentioned before that there are computational challenges associated with doing these risk-based event set assessments. So one, for example, a typical simulation takes anywhere between 2 minutes and 6 hours. So remember, we need to sample, we need to generate all realizations of our ground shaking maps. So we're talking about 2,300 times 1,000 damage maps. And then from that, we would simulate the recovery process, meaning the actual repair process. And then we need to link that to the hydraulic simulation, which also could take a significant amount of time. So depending on the level of damage and how much is damaged, one single end-to-end simulation can take anywhere from 2 to 6 hours. Now, we did use parallel computing, so that helped a lot. But, you know, I mentioned that in this case, we actually considered the USERV2 scenario, which only has USERV2 model, which only has 2,300 events. Well, the USERV3 model, which came out within the last 5 years or so, has the number of events increases by a factor of about 100, right? So you can see how the computational event expense could scale up significantly. You can also, if you have a larger system, so we can compare the Napa water system, which has about 600 kilometers of pipe, the Los Angeles County water system, which has over 12,000 kilometers of pipe, right? So when you start scaling the system up, then, you know, the computation expense increases significantly. And then there are some type of network performance metrics that we didn't consider here. So things related to centrality measures, like betweenness centrality, meaning how much is the damage or the loss of service distributed to the system or centralized in particular locations. So those types of metrics actually take a lot longer to quantify. So one of the things that we got into was using a technique called active learning that allows us to select a subset of events such that running the end-to-end simulation on that subset would give us approximately the same results as if we ran on the entire suite of scenarios. So just a quick overview of the active learning framework. So you start by defining some instance or input distribution, and then you would have to query. So you would query the larger set of events, and there's different techniques available for doing that. In this case, we use pool-based sampling. Then you have an oracle that sort of says, okay, based on these inputs, we use a Gaussian process model to get us to the outputs, and then we have some criteria for saying, okay, let's select a new subset of events that's actually associated with the highest level of variance, and based on that, we can sort of repeat this process, and we have a stopping criteria that tells us when we can stop sampling. Now, if we put that in the context of, well, before I get into the specific application, I mentioned there's a stopping criteria that's based on so you have a specific threshold, variance threshold that's compared to the variance over the subset that the top M part of the selected subset that has the highest level of variance. And so you compare that with a variance threshold, and you use that as your stopping criteria. So how does it work for the map selection? Well, you select your initial subset of maps, and you can do that randomly. You would run your end-to-end simulation. You would build a Gaussian process model. This model would link some measure of the shaking intensity to the overall performance metric. And then you would check for your stopping criteria. And again, we use uncertainty sampling, meaning we compare the uncertainty in the top M selections to some criteria, and if we satisfy that criteria, we stop sampling, and if not, we select additional samples. And so what's shown here is the active learning performed on the metric of time to restore 100% of the pre-event SSI. And we're showing sort of the evolution of the R-squared value, which is basically, you can think of that as sort of the measuring the relationship between the annual rate of exceedance curve from the full data set, which is listed as empirical, as well as the selected subset. So we can look at some numbers here. So first of all, we did this for the three metrics. So if we first look at the diagonal, it tells us that, so remember, we're dealing with about 2,300 events. So if we look at this particular location, this tells us that about 920 of the 2,300 events, we can estimate the SSI hazard curve with an R squared of about 0.9. And for the 100% SSI, it's about the same number of events, 920, but if it's the cumulative loss of SSI, we can do it with even a smaller number of events. Yeah, so that's the diagonal. The other thing we wanted to say is, okay, well, what if we selected a set of events based on SSI, for example, and so this says, okay, we do our selection based on SSI, and then we say, okay, we take those events and we try to predict we do our selection based on the immediate loss of SSI, and we take those events and we use that as the starting set in the active learning for 100% SSI. And what it's saying is that we're pretty much, we can pretty much only need a single additional, and that's really just to do the check. So it pretty much says if we select a set of events based on the immediate loss, then that set of events is likely going to work for 100% SSI as well as the cumulative loss as a SSI. However, if we select a set of events, say based on the cumulative loss, then we need an additional 113 to get to the immediate loss of SSI, and we need an additional 684 to get to 100% SSI. Okay, so in this last few minutes, I'm going to talk a little bit about how we developed a framework to use data collected during the recovery to actually update our predictions of the recovery trajectory over time. Right, so I mentioned that we have all of these sources of uncertainty that we considered, and I'm a little bit more specific here, meaning it's a little bit more disaggregated here in terms of the type of uncertainty. And so we want to say over time, as we sort of collect information on what's damaged or how long things take to get inspected or how long things take to get repaired, can we update the distributions of the parameters and sort of and as well as update our estimates of the recovery trajectory. So really quickly, I'll give an overview of how this works. This slide is going to get pretty busy. So we have all of these variables that we are considering, right? So we have our fragilities that are used for pipe damage. We have the parameters that are associated with the repair time. We have the distribution of the inspection and repair crew, and then we have how long it takes for things to recover, right? And we do our simulation, right? So we have our simulation model, so we can do a simulation at any time, right? And then as time goes by and we're sort of during the recovery process, we have observations that we can use to actually update those parameters that go into our simulation model. So if we take two snapshots in time, one at day 0 and one at day t, we can look at, we can have a priori on the pipe damage distribution, meaning we're just using fragilities from that we developed or fragilities from hazards or wherever the fragilities come from. And then we have priority distribution on the repair time, meaning we have maybe data from past events or maybe even past, maybe even other water distribution systems that we use to approximate the distribution of the repair time, as well as the inspection crew, right? And we look at two alternative approaches. One approach is we develop a Bayesian network model of the pipe networks of the pipe network, and that allows us to compute the total recovery duration. And so given information collected over time, well, so the other type of model that's shown here in the yellow is the DES model that allows us to update not just the total recovery time, but the entire recovery duration, the entire recovery trajectory, right? So between day 0 and day t, we have some observations, right? So some pipes we've observed, so maybe some of the pipes we simulated as damaged, we observed them and actually they're not damaged. Some of the pipes that we simulated as undamaged, maybe they were damaged. So we have some information that we can use to update our parameters. Similarly, so maybe some pipes have gotten repaired, some pipes, there's some changes in the inspection crew. So we can take that information and use Bayesian parameter estimation to get a new Bayesian network model, as well as we can put those updated parameters into the DES model and get a full recovery trajectory. So some quick results on that. So this just shows, so I mentioned there's two ways that we do this. One, we use a Bayesian network model on the pipe, for the pipe network, right? And so this shows that network model. So so you have the pipe type, the damage feeding into the repair time. You have an indicator of damage and the repair time feeding into whether or not the pipe is recovered. And then the network on the left is for a single pipe. And then we use a plate model, which basically is replicating the network for the individual pipes across the entire system, right? And so what we see here is how the distribution of the total repair time for the pipe network evolves over time, right? So on one horizontal axis is the time after the earthquake, and on the other horizontal axis is the distribution of the pipe recovery time. And so as we move along the days after the earthquake, well, one, we see the distribution, both the central tendency and the dispersion of the distribution is changing. So the location or the central tendency is moving, but the dispersion is actually being reduced, and that's just based on information that's collected over time. So the other approach we used was actually we would just take the parameters that are input into the PBDS model, so things like the pipe repair time or the pipe inspection time, and we would use Bayes' theorem and Bayesian parameter estimation to update the parameters that go into the PBS model. And so what's shown here is how the simulation evolves over time. So what we're doing here, so the black line actually represents the observed pipe trajectory for the Napa earthquake. And the gray lines, what we're doing is, it's probably a little bit hard to see, but each of the gray lines represents a simulation of the recovery trajectory at some point. So for example, 10 days in, we actually use the information from day 0 to day 10 to do a recovery simulation from day 10 forward. And we sort of keep stepping forward. And so as you can see, as we move forward in time, the simulated trajectories start to align well with the observed recovery trajectory. And the plot on the right just shows how the residual sum of squares between the simulated and the observed sort of reduces over time. Okay, so just to quickly recap, we developed this end-to-end simulation model that can be used to inform both pre-event and post-event decisions. What does that mean? Well, that means it can allow you to say, okay, does it make the most sense to sort of harden my pipes and my pumps and things like that to avoid damage, or am I better served sort of putting things in place, materials and different other types of resources to support the recovery, right? So it allows you to look at both pre and post-event type of decisions. We looked at not just a single scenario, but the full spectrum of scenarios that can affect the region, and that allows you to do it allows you to evaluate things using life cycle performance metrics. We use this technique called active learning to do a type of smart sampling where we don't have to evaluate the performance for every single event. We can choose we can adaptively select a subset of events such that we would get a final distribution that well approximates what you would get with the full set of events. And then finally, we looked at sort of this real-time forecast model where we can update our recovery trajectories as we move forward in time and collect information about the damage and the recovery. And with that, I will open up the floor for questions.
We do have a question in the chat box, and I will go ahead and read that for you. Thank you for the outstanding presentation, Professor Burton. I have one question related to slide number 28. Do you have a way to evaluate the sensitivity of the overall resilience model? I'm a bit concerned that the errors in each submodel would propagate into the overall model and wonder how you can minimize such a risk. Or maybe the question is more about the validation of the model predictions. Could you comment on how the model was validated?
Yeah, so that's a great question. So I think it sort of points to a broader question of these especially large scale simulation models, where you're trying to capture a lot of complex interacting processes. That's one of the reasons why we actually propagate the uncertainty, and so we can actually show the uncertainty bounds on the simulation model. So to answer the question about sensitivity, the answer is yes. We can look at the sensitivity of the overall resilience to individual parameters. And that's, I mean, I would argue that's kind of what we did when we looked at the sensitive. What we looked at was the sensitivity to different types of uncertainty, right? So for example, I mean, you call them errors, I would call them just uncertainty in the various parameters, right? So we looked at, okay, if we were just looking at the sensitivity, if we were just looking at the uncertainty in the shaking, sort of what would be the distribution on the recovery curves, or if we were looking at the sensitivity of the damage fragility, how would that affect the overall distribution? So I think this type of disaggregation of uncertainty gets to that question about the sensitivity analysis. Now, I think I mentioned before, there's sort of this larger question that I think is being inferred here, which is sort of, how do we use these models? How do we use it to inform decision making without sort of projecting overconfidence, right? Because again, there's a lot of variables in these models. It's a very complex system. Some of the parameters that go into the models are not as well calibrated, and so what I would say is, a lot of times when we think about these models, we want to think of it as, well, one, we want to be able to say, okay, at least it captures the overall shape of the recovery, right? Which we've shown it does, not just for this particular system, but if you look at sort of observed recovery trajectories for buildings and things like that, it generally gives you sort of that, unless things are really bad, you kind of get that exponential type of recovery, at least for systems here in the US, right? So the first thing we can say is, we're capturing the overall shape of the recovery, right? Now, it's not going to be as precise. So you say, well, how would you use this model? Well, I would say you would primarily want to use it to understand how changes in different parameters actually perturb the overall system. So for example, the question you'd want to answer is, if I change my damage fragility parameters, which is actually associated with hardening your system, how much change in the recovery trajectory do I get? Right. So then now it's more about the absolute change in it's not more about the relative change in the recovery trajectory as opposed to the absolute numbers. I hope that long-winded answer somewhat covers your question. Let's see. Okay, yeah. So I think that was a two-parter there by Professor Shi.
Yes, it was.
Great question.
Yeah.
And it's one that always comes up and will always come up with these sort of large scale simulation models.
I don't see any other questions. We can wait a couple of minutes if you'd like.
Yeah, that's fine.
Just thank you again for your time and a really great presentation, really well explained and very beneficial. We'll have a lot of people who view this once we get it up on our YouTube channel. So,
sorry to interrupt, Professor Burton. Thank you for the presentation again. Since I have a student who's more specialized in data science,
yes,
and his PhD topic might be related to resilience.
Yes.
Do you think data science would be beneficial? I mean, the skill set would be beneficial in this type of resilience analysis?
Sorry, what type of science?
Data science.
Oh, absolutely. Data science. Oh, absolutely. Absolutely. In fact, the active learning model, actually the student who, Agam Toma, our former student who implemented all of this, he took a lot of classes from statistics and electrical engineering, which were absolutely useful for, especially all of it, but especially the active learning part, where, as I mentioned, it relies on this Gaussian process regression model. So absolutely, I think data science is, I would say, it's a necessary skill set.
Thank you.
All right. So it looks like we're
Yeah, I don't see any more questions coming across.
All right.
Are you all right if I put your contact information on the video?
Sure, absolutely. And
Thank you.
if you can share the link with me when you post it to
Yes.
YouTube, that'd be great.
I absolutely will. Thank you so much. We really appreciate your time.
All right. Thank you again for the invitation.
Yes, and thank you everyone else. Bye now.